Okay, good morning everybody. It's great to see you back today. Hope you enjoyed the practicals in the afternoon yesterday. There's plenty more where that came from. We always, as we say all along, we're keen to hear your feedback along the way. So let us know at morning tea and lunchtimes how things are going. Before I forget, because Belle always gives me a list of things to not forget, so I'll start with them. We've got the industry tours to Rapier and Codan today, and we have one spot. There'll be a rush forward. Yep. Done. There's no spot. Yeah, how much is so? No, yeah. Are you on there too, Simon? And a reminder. And see, this is what Belle's just wonderful, isn't she? So the spots full. Yes, meet near the food for the tour at 12:05, around 12, so that we're all in the same place to get on the bus to go, and we can make the most of the time at the tour. OptoFAB visit is tonight, 6 to 8 p.m. We have some spaces there. I can't remember if there's pizza. Is there pizza this time? There's pizza this time. So there's 15 spots of pizza available, plus a wonderful tour of OptoFAB. So I would really encourage you to go and see them. They're a sister facility. I mentioned that before. They complement a lot of the capabilities we've got here, and some of the speakers that you see online tomorrow because of the public holiday are based at OptoFAB. So please sign up and join that. Okay, so it's like being on TV with but what I want to forget here is that, hang on a sec. Is this changing? Yes. Okay. I also wanted to start by acknowledging country here. We're on the lands of the Kaurna people, and we understand a very strong spiritual connection and cultural connection to the lands, and also as an education opportunity here today at the Winter School, we also acknowledge that over many years there's been education and knowledge that has been shared through generations, and so we acknowledge that today. I think you all know where the toilets are, hopefully from yesterday. You all know what to do in an emergency to evacuate out to the grassed area and follow instructions. This morning we will start with do you want to do the sponsor now? Yeah, we're doing the sponsor now. Okay, we're going to go straight to a short, I'm tempted to say commercial break, but a sponsor break. We'd like to show the video. It's me showing the video, is it? Okay. All right, let's see how we're going to multitask here. So, is it this one? It's the flamethrower, right? Okay. All right. I actually have no idea what I'm about to show you. Full
this
screen.
Is Evident and Olympus.
Evident and Olympus, excellent.
We're wonderful sponsors.
Here we go.
We've got sound.
And skip the ads, right? Yeah. I'm not sure we're showing sound. Why is sound not coming? Let me pause that for a sec.
That is a very good question. Can we just go out to share screen again?
I think it's the room.
Okay.
Audio is up.
Just me. Okay, if we click on that, and we got share sound.
Okay.
Yeah.
There we go.
Thank you.
Now we're good. Let me take it back to the start. But we are very grateful for our sponsors, and so we'll just take this moment to look at this video, and then in the break I expect you all to buy some Olympus gear, all right? Hopefully this works now. Did I do that wrong? There's no sound.
Maybe there's no sound.
You know what? I'm going to pause that. We're going to make sure we sort out the sound. We'll come back to that. But still buy some Olympus gear in the break, all right? It's your job today. This is me. Excellent. Okay. Well, that was very smooth. So we can make micro devices, but we can't work the sound. Yeah, look, I just want to remind you that this is a great opportunity to network and talk and meet with each other. Enjoy the pracs, get to know tech staff. We also have two wonderful guest speakers this morning. Actually, we've got four wonderful speakers. Three of them have come from elsewhere to speak to you, and Donghoon is also amazing. He's based here in UniSA. And you will have met him in, well, you will meet him in one of the pracs. But this morning, the first two insight talks are from Professor Michael Breadmore at the University of Tasmania, and Allison Love from Fertilis, which is a startup, a successful startup company that is using the up nano two-photon printing capability that you might be able to see in the tours here on campus, which is brand new capability and world's best. So get to know both of these speakers this morning. I think we can move straight to the first talk, yes, which is going to be Michael. So I'm just going to switch out to Michael's presentation, which is not open yet. That's right.
That's right, not open yet.
It's all good. That's all good. Don't panic.
I'll tell you that.
I know. We're all good. And is it in? It's on the desktop.
It's on the desktop.
All right. So I should just be able to go in here and do this. Desktop. Hopefully. There we go. There's my Zoom. Very smooth. Okay, this is Michael Breadmore, and there's the slideshow. Okay, so now Michael always has a laugh when I read his bio, because Michael and I have known each other for 1,000 years, but I'm going to do it anyway, because this might be the only joy that...
I'll sit back down.
No, just stand there. I want everyone to look at you while I read it rather than look at me. Now, Michael and I have known each other for many years. We are both microfluidics researchers and lab on a chip and sensor, and we're both chemistry people. And so what I want to just say is that Michael has had an ARC Future Fellowship. He's had a QE2 Fellowship. He's had an ARC APD, which is, I think, the DECRA, from long ago. He has a national and international reputation for the development of new and novel portable analytical devices and systems with more than 180, it's probably even more now, this is old, isn't it? It's probably, so there's, 1,000 publications, peer-reviewed publications. His research has been published in leading journals. He works with companies to perform fundamental and translational research, with the most recent product of his research based on his research Grayscan, released for global sales in 2018, but also is award-winning, an award-winning technology in the Eureka prize many years ago, which is a really nationally significant award. So we have an award-winning leader in the academic sphere, but somebody who is translating their research into industry. And as we saw with the NASA speaker yesterday with Harry, he talked about the TRL. So people like Michael have taken ideas at the bottom of the TRL right through the top of those TRL scales where they've entered into the real world as products and benefited society. So we're very privileged to have you with us, Michael. We're looking forward to hearing what you say about microfluidics and lab on a chip and pretty much anything else you'd like to tell us about. Thank you.
Thanks, Craig. It's always wonderful to hear the things I didn't write about myself on the bio, so thank you for that. I'd like to begin by also acknowledging the traditional owners and custodians of the land upon which we stand today, but also upon which the land in which all the work I'm going to talk to you about today is, and that is also across this country, but also other many countries around the world. So as Craig said, we've known each other for a very long time, and despite the looks of that professionalism that you saw this morning, trust me, they are much better at making stuff than doing tech and video presentations. And I don't know why Craig just didn't hand over to Belle. She would have done a much better job anyway. Craig always asked me to come and talk about lab on a chip and microfluidics, and that's what I'm going to do today, and try and give you an overview in the next 25 minutes or so of some of the capabilities and the things you can do, and very little of that is which I've done, because the stuff I've done is pretty boring. So I'm going to start with at the beginning, where all good stories start, and this was at the end of the 90s. On the slide you'll see Professor Andreas Mons, who was at a company called Siebergeige in Switzerland, and the whole premise of his idea was to take all the technology from the microelectronics industry, where we make silicon microchips and they're really awesome, and to do that for the chemical laboratory. And so you can see him holding this little thing in his hand. He called that a lab on a chip. And in that you're going to have lots of little people, and those little people are going to be doing all the things that you would do in a chemical laboratory. And so that's the dream, is to take that integration of what happens in the microelectronics industry and to do exactly the same for the chemical and the microbiology industry, because if we can do that, we can save the world in so many ways. And there's a few reasons of why we want to do this. If we scale everything down, it becomes so much quicker, because, you know, obviously if you run a kilometre running race, it takes you a lot longer to run 100 metres, and it takes less time to run 100 metres and less time to run 10. So if we make everything smaller, then everything happens quicker. Because it's really small, it's really portable, so we can take it wherever we want. It's hopefully really cheap if we can scale up all of those things from the microelectronics industry, which make our mobile phones and our computers really cheap and usable today. We can use really tiny volumes, and by tiny volumes, we're talking microlitres or even nanolitres. Right? So we don't need to sample hundreds of litres of something, we only need very small amounts, and that's really advantageous if you have something where you only have a really small amount, such as inside a cell. And ideally, if you get all of this right, it can be used by anyone, anywhere, at any time. That's the dream. The reality is that we're often a long way away from the dream, but we are getting closer. So this was one of the very first applications where that whole process was translated for speed. And so you can see here an analysis of some amino acids. It's not particularly exciting at this point in time, but the bit that's important is that bottom bit there on the separation, which shows 20 seconds. So we're doing an analysis of 7 or 8 molecules now in 20 seconds, which is really exciting, because before this it would take 5 or 10 minutes. The reason that this is interesting is because we can now make it to do a whole heap of more amino acids. And then this slide on the right shows a real-time profile of neurotransmitters inside a rat brain while the rat is being exposed to some dopamine. So you can see my red dot on that slide. The infusion starts at about 15 minutes, and then you can see the asp and the glue come up, and some of the other things change. And this is all real-time, so it now gives you the chance of being able to monitor brain chemistry real-time. And because it's really quick, it's real time. Because it's really small, you can actually stick it in a little backpack on the rat. And because it's really small, it actually doesn't use very much of the rat fluid to be able to do that. So all of those advantages that I talked about. That's one of the reasons it needs to be portable. But I also said that you could take this anywhere and do anything with it. And so this is some work that was done, I think it was out of Berkeley, and then transferred to the JPL lab in Pasadena, looking for amino acids again, but this time to send to Mars. So this is the Mars amino acid analyzer. It's a microfluidic device with 4 layers, very, very complicated. You can see the instrument that houses it there on the right. Really quite powerful, really quite nice, really quite expensive. So I don't know what was at the NASA talk yesterday, but these guys have got a budget, or their cost is going to be about $500,000 to build this thing so they can send to Mars. Now, I don't know about you, but I don't have $500,000 to build one of these. I'd like $500,000, but even if I had $500,000, I wouldn't build one of these, I'd do something else. But if you're looking for life on Mars, this is the only way we're going to get there, because all the other stuff they've sent so far is not fit for purpose. So this is where being really small, being really tiny, using lots of small fluids is really good, because it's really expensive to get stuff to Mars, right? So that weight becomes important. And that's just some experiments there where they actually took it out to one of the deserts. I can't remember which one it is, and actually showed that this whole thing actually works. And I believe it is intending to go to Mars at some point when they're launching something somewhere. I don't know when. I haven't seen Pete talk about this for a while. Oh, too fast. The whole problem we have with all of this miniaturisation, though, is we get the chip in a lab syndrome, not the lab in a chip syndrome. So this is illustrated in this picture, right? Ideally, we want everything we can hold. The reality is that you get a spaghetti factory that costs you $500,000 to send to Mars. And if we can actually start and integrate with better manufacturing and different materials and all these kind of things, then we can actually get to our dream. And so there's a few people that are working towards this. So this is one of my colleagues, Roseanne, who's now a deacon, and she's looking at how to integrate manufacturing. So not to make one-off devices, but to figure out how that we can make multiple devices which are highly integrated and feature lots of different capabilities in a really seamless way. And so this is one of the work that we did with her on 3D printing and being able to manufacture something with 5 different materials in it at the same time means that we can actually eliminate a lot of the manufacturing steps, of which some of which you'll see at ANFF here today. The only problem is we can generally make 1 or 2 of these at a time, as opposed to what you'll see here, where you might be able to make hundreds at a time. So different scales, but perhaps different purposes at this point in time. One of the other major challenges is how to move all of these things that we want in there. So fluids, in particular cells. And so this is some work by Mohammed Shadiqi at Griffith, looking at using electric fields. But the neat thing they've done here is they have asymmetric electrodes and an alternating current. And I don't understand the physics behind this, but apparently what this does is, because of the different size of the electrodes, it causes the fluid to only go in one way, even though you change the direction of the electric field. So pretty neat, pretty simple. And there's also some other unique phenomena that occurs around surface fouling, so that you don't have any problems with protein sticking, which is also a pretty neat byproduct of what they were trying to do. An even easier approach is to use something that has been around for decades, and that is capillary action. And so in my field as an analytical chemist, we used to do paper chromatography. You've probably all done that, where you put a little bit drop of ink on a piece of paper and you put it in some liquid and the colours run off the page, and you can separate black into blue and green and yellow. The same thing here. We can do exactly that same process and use the capillary forces in the paper to move fluid. And so paper chromatography was old in the 90s, and then someone decided to do this for microfluidics, and all of a sudden it became really popular. And so you can see some of the very early stages here in 2010. There's a glucose and a BSA, bovine serum albumin assay there, just to show that it can be done. But paper fluidics has become a really high-profile, low-cost method of doing chemical analysis. And it's really good for regional areas where you don't have a disposal chain, because you could burn it and you dispose of everything that way. Maybe not so good for global warming, but it means that you don't have to dispose of it in a different way. And if you're handling biological samples like blood, then you're also removing your biohazard. There are some things, though, that I don't think you'll ever be able to do on paper. Maybe, I'll be wrong, but I think that paper does have some limitations, but it is still useful. This is one of my favourite papers from Wei Shen at Monash, and it was inspired from Harry Potter. Do you know my blood type? You know, Harry Potter, the first, is it the Chamber of Secrets, where the book writes? Well, Wei Shen decided, can I get my paper to tell me the answer? And so when you put blood on there, it will now tell you whether you're A positive or O positive or A negative. I don't know all my blood groups, I don't know what they all are, but the paper will tell you. And that's really neat, because if you're in an emergency situation, you don't have to interpret. You can just read the answer, right? It's completely intuitive. And they've also extended this now to heavy metal detection. And so depending on what you can see, if you can see the colour, if you can read the copper, you've got a copper problem. right? So again, making really simple, really intuitive measurements. Using the eyes here, so again, we get rid of all that lab on a chip in a lab syndrome, right? Because we are the lab, all right? We've all got eyes. And the other thing that we've all got these days are mobile phones. And so Connor Hogan at La Trobe started using a phone to be able to do a lot of these things with microfluidic devices. And so in this case, is doing some light generation using the audio output from the phone. That's a bit more of a problem these days, given that most of our phones don't actually have an audio output anymore, and it's all Bluetooth. And then using the camera and actually also the audio input to be able to get the measurements back in. So that's really cool, but again, the problem with that, as I've already alluded to, is as the phone makers keep changing the phones, we got to keep changing how we use the phones, and that is challenging sometimes for us to just keep up with how things are changing. Okay, so I'm an analytical chemist and I love measuring stuff, but there has to be, and there is more than that. And so one of the great things, or the unique things about microfluidics, is laminar flow. So you can see that here with these three colours. You'll see that as you change the ratios in those fluids, indicated by the numbers on the slide, the thickness of those lines change. They don't mix, and that's because it's laminar flow. Right? So the constraints of the dimensions mean that the fluids don't mix and they stay as they are. And that's really neat because you can do some things like look at really small things up close and have really bad pictures taken, like Craig is illustrating there wonderfully. And doing that, you can do some liquid extraction. So Craig has done some work talking about extracting minerals from a water processing stream into an organic acceptor stream, and maybe being able to use this for mining, refining purposes. And then you go, well, hey, it's really small. And you go, well, actually, it doesn't matter if it's really small. I can make 1 billion of these really easily. So then I can get to large scales, and my physics, my laminar flow stays exactly the same. My all-time favourite example of laminar flow is this one here, and it's a sperm sorting chip for IVF. I think I need to play my video again, but it's really, really simple. The sperm come in at the top. If they are not very active, they stay in the top. If they're highly active, they swim down across the stream into another stream, which is moving much more slowly, and then you can collect the high motility sperm. And so this is a really nice way of selecting sperm that have a high viability for in vitro fertilisation. I saw this first, I think, in about 2005 or 2006, and at that time, the first babies from this had been produced, and then the company, I believe, did spin out after that, and I think it's still successful, but I honestly haven't kept track of that side of things. Still, I think one of my favourite examples of really simple fluidics. It gets more complicated than that, and because, again, it doesn't mix, we can do things like creating an artificial spleen. So this is for removing bad things from blood. We can put something in there that has a magnetic particle on it. It attaches to the bad things, the pathogens, the toxins, and using a magnetic field, we can strip them from the blood into that acceptor stream. And because it's laminar, the blood just goes straight back out again. And we don't have to dilute it, we don't contaminate it, and it's really neat. And this was actually funded by a very large grant in the US for military. So how do you treat someone in the field? It has to be really small, has to be really portable, has to be really simple, right? So you can't take 10 litres of blood to give them an infusion. You have to use what you've already got there. And that has, of course, spurned a whole new area of what's now called organs on a chip, tissues on a chip, humans on a chip. The Human on a Chip project is designed to take every functional part of your body and to put it on a microfluidic device or a series of microfluidic devices so that you can connect them all together exactly the same way they work in our body, and we can then start and do experiments, not on people, not on animals, but on microfluidic devices. Still a fair way to go yet, but we are getting much, much closer, and maybe one year I might actually get to actually have a picture of what that looks like. It'll probably be pretty big for the moment, but I think before I'm dead, we'll probably have that somewhere. In Queensland, in terms of tissues on a chip and culture on a chip, Justin Cooper-White is doing some really nice things with stem cells. These were very interesting maybe about a decade ago, but one of the neat things that they were doing was looking at how stem cells evolve. And so they would culture stem cells in a series of chambers all interconnected. And as the first stem cells would change, the chemistry that those cells would then release would influence how the next cells evolved and changed, and the next cells. And so they were starting to look now at how the stem cells evolve into different types of cells that we have in our body, and how the previous cells or the microenvironment around those influences that. And that's really easy to do on the microfluidic devices because we can actually look at individual cells, we can actually control all the chemistry really nicely, and we can cascade them in any way that we would like. Also, speaking of cells, Majid Wakiani at UTS has been doing some really nice stuff on circulating tumour cells. So these have been recognised as an important part of the spread of cancer, particularly after you've had surgery and you've had your cancerous tumour removed. What they have now is a device or a series of devices that have been commercialised to actually remove all of the circulating tumour cells from your blood after surgery. So they'll take you out after surgery, they'll connect you up to, I think it's about 10 microfluidic devices all stacked on top of each other, and over the course of a couple of hours your entire blood is filtered through this and it removes 100% of the circulating tumour cells to hopefully stop and minimise that risk of spreading the cancer throughout your body. So that's commercial. I don't know how viable the company is, but I think they're going to do really well because I think it's a market that's not going to go away anytime soon. And also separating particles and cells is David Inglis at Macquarie, using what's called little posts. These posts are offset and they're called bump arrays because as your particles follow flow streams and they hit this post, it moves a little bit into a side. And so you progressively bump particles of different sizes into different parts of your device, and you can separate particles based on size really.
Recording stopped.
Uh-oh, what did I do? Wasn't me. I didn't touch anything. We can even do chemistry too. So that's all around, particles analysis. So this is a really old example now of doing chemical reactions in microfluidic devices. And that's nice because as you scale everything down, everything gets quicker. So reactions that take hours can now be done in seconds. And we can do them in series and add different reagents at different time points and automate that entire chemical synthesis process. Hey, you broke my slide changer. What'd you do? Sabotage. I was giving them nice compliments about being professional.
Yeah, you probably deserved it, Michael. Is it working now?
Yeah, it's working now.
There we go.
So one of the other neat things I think is neat about microfluidics is that you can now do things in really small volumes. So these are nano droplets. So in micron-sized channels, by changing the fluid geometries and mixing or using different fluids, so these are the green and red fluids here are miscible with the colourless fluid that you can't see. You can make little drops, and then you can mix those little drops as you can see there. And then you can take those drops, you can combine 3 drops, and then you can split them at the bottom, and then you can capture the offset, and then you can combine those 3 drops and you can split them again, and you can do this as much as you would like. You can capture drops. So you can capture 1 drop, 2 drops, 3 drops, 4 drops, however many drops you want, and then you can sequentially release these drops or access whichever drops you would like. So you might do some reactions, and then whichever one you can see the products in, you can then access and analyse or do something else with. And you can't just do that on one, you can do that on millions of drops. So the droplet rate, or the rate at which droplets are generated, is typically 100 drops a second, up to about 1,000 to 10,000 drops a second. You can do individual reactions in each of these droplets, which is pretty exciting given that each of them is completely separate until you decide to put them all together again, right? We decide what happens by the design that we use. And one of the areas that this has become really important is for DNA testing. So one of the problems when you have a rape case, for example, is trying to find that 1 or 2 sperm cells in amongst millions of the female epithelial cells. And if you can actually separate each of those cells into their own droplet and do the analysis on each droplet, you actually remove a lot of the background and make the identification of the sperm cells or finding the male DNA much, much easier. And so that's come out of Berkeley, is currently commercialised, and I think is also going to be a really good product because they're not going to go anywhere soon because the number of bad people in the world doesn't seem to be getting less despite our efforts to try and make it so, which is a little bit of a sad reflection, I think, in many ways. If you only want 1 drop, Adrian Neal at Monash can help you with that. So he uses some surface acoustic waves from the little electrodes there. And by actuating those at particular times, you can produce 1 drop, 10 drops, however many drops you want, when you want it. So this is a different way of making drops, and then you can do all of those other manipulations with them that I just talked about. Also using acoustic waves is Leslie at RMIT. He's done a whole heap of things with surface acoustic waves. So this is one of his earlier works now looking at centrifuging stuff, but has done a lot of stuff recently in terms of droplet.
Recording in progress.
How much time do I have left? I won't ask Craig, maybe I should ask Belle. 7 minutes, right? Okay, I think I'm nearly at the fun stuff anyway. And then also on droplets is Nam Trung at Griffith, who's doing some interesting things with liquid marbles. So the example on the right there is a drop of liquid that balls up on the surface because it's hydrophobic, and then he's then coating that in nanoparticles, and that creates that liquid that's completely impervious. You can then, and I can't find the videos, but you can then use a magnetic field to move these all around. You can use magnetic particles, or you can use a magnetic fluid. The one that I saw with the magnetic particles, you could actually make the droplets, the particles all come down on the side of the droplet, so you could access the fluid, and then when you take the magnetic field away, the particles go back up again and seal it in. Really neat stuff, but I can't find the video, so I'm going to have to contact him and see whether I can get that from him. If I ever get to do this talk again, which I probably won't because I'm bagging Craig out too much. And so that's the basics of microfluidics. Now I've got about 5 minutes to show you some other stuff that I think is really cool, but I'm going to give you the choice. So I've got jump to end, so we can stop and you can have a rest and we can pass on to Allison, or electrowetting drops, pyramids, robots, or screens. What would you like to see? Who wants to see anything? Which one do you want to see? Someone tell me something. Robots. Robots, awesome choice. My favourite, well actually they're all my favourite, otherwise I wouldn't have them here, right? I love the funky music. It's not my first choice. This has come out of Harvard and the Whiteside group. It's a soft robot, the OptoBot. Maybe I'll stop. That's really neat stuff, right? And it's also actually not that complicated despite what it looks, and could actually be done here, couldn't it, Craig? Yes. Right, so a lot of the stuff there that you saw in terms of that liquid going in, degassing, that's all just essentially making PDMS stuff, and you're going to do that in the labs, right? You don't do the 3D printing inkjet stuff, but you could do that because you've got 3D printers, right? Sorry, I'm not even going to ask Craig. But so there's no reason why that had to be done at Harvard. That could equally be done somewhere like here if we were smart enough and ambitious enough. And I'm looking at all the young people, young enough to actually want to make stuff like that, because you guys have got the imagination to be able to make something a little bit more useful, I think, than an Octobot. I don't know what that might be. I think my Vice Chancellor saw that and actually wanted a little thing that you actually touch apples to see whether they're ripe. So, you know, some tactile soft robotic sensors so that you could determine when the apple was the right time to pick. And then if your sensor's integrated, then you can just automatically pick it and chuck it in the bucket at the same time. And if it's not, then you just leave it and move on to the next apple. Right, so there's a lot of possibilities there that are not particularly hard. How am I going for time, guys? I'm about done. Okay, so. Oh no, I missed my acknowledgement slide. Right, can I jump to that? I, of course, always need to acknowledge the funding for people letting me do fun things like come here and talk to you, and that's primarily the Australian Research Council. And of course, I do need to thank Craig for continuing to invite me, even though I keep bagging him out every year and I keep going harder and harder, and he still keeps inviting me. So next year I've actually got to go even harder again. And to Belle, who of course organises everything exceptionally well, and I don't think would run if it wasn't for her, even though Craig thinks he's an important person. So thank you very much. If there's some questions, I will answer them as best I can.
Thank you, Michael.
You always forget.
Thank you for your wonderful talk, but we would like some questions as well. So
I'm just going to eat chocolate. No, I'm not going to eat biscuits.
Ask Michael how to make an
I don't know how to make an octobot. Craig knows how to make an octobot. The team here knows how to make an octobot, not me. Did anyone have any questions? If you don't want to ask now, you can come find me in the break, but I apologise that I am going to have to leave after the break to go home to collect my child from work. So the break will be an hour, the only answers you'll get to talk to me face to face. I think they're all scared. They're scared I'm going to bash out on them like I did you.
We haven't had a question, but we have had a comment saying very cool things.
Go, praise that.
So there must be a question. Let's try and get one out for somebody big.
I guess I'm not a chemistry or a biology guy. I love that flow. Curious, we've got two mixtures side by side and they're not mixing.
Yeah.
You still get a good bit of molecular interaction on the interface of the two?
You can. Depends. So, really good question. So it depends on the size of what you're in there. So small molecules or small ions like chloride will diffuse very quickly into the other side. Proteins will diffuse about maybe 50 to 100 times slower. And then particles, so maybe a 1 micron or a 10 micron particle will diffuse even 100 times slower than that. So by controlling the flow rate at which you go through, you can actually control the extent of diffusion of whatever you want from one side to the other. That makes sense? And you can actually use that really nicely to do some filtering. So you can actually remove proteins from some samples by selecting the right flow rate. If you want proteins and you don't want cells, you can also select the slightly slower flow rate so the proteins diffuse but the cells don't. So really quite interesting. And then depending on the properties of the fluids, you can then do some other interesting things. So really, really nice question. Thank you. The answer to that, I think, depends on what you want to do. So I have some colleagues who buy some chips that we could make them, but it's just easier to buy them for culturing neurons. And there's a small company that was set up in the US to just, they published the paper in Nature, they then set up the company, and then they just started selling these chips to neuroscientists around the world, and everyone just buys them. They go, cool. In that case, it's just easier to buy them and actually cheaper to buy them than to make your own. But we've also been working with them for the past 5 or 6 years making devices which they can't buy because they now want to do stuff that the commercial stuff can't do. And so starting out, if you can get it commercially, I would say go for it. But you will probably reach a point where that commercial device will not do what you want. And it might be 6 months, it might be 6 years, but you will get to a point where you want to do more, and then you have to talk to somewhere like here to be able to help design and construct what you need. And so that's one of the good things about ANFF here is that it's almost a one-stop shop, right? So they'll help you do everything you need, from design through to manufacturing.
Allison up and we'll just see if we can do the IT. See how we go. This is you here, I think. Oh, okay.
Awesome, thank you.
Just a moment. I'll have to introduce you as well. But I just want to make sure the IT was working this time. I guess one other comment, I like to try and draw some links between some of the presentations and the practicals and the other things that happened during the school. If you've done the PDMS practical yesterday where you made some microfluidic channels, some of that laminar flow and maybe some bubbles and things, but also the PDMS, the soft materials, would be something that you've seen. Now what you did in that prac is how you make some of these sorts of devices. You saw the bubbles coming out during the fab. And so what Michael's been talking about and what you're learning in the prac are actually closely linked. So if you're interested in making microfluidic devices, by far PDMS devices are the best way to sort of get your hands dirty or sticky, actually, with PDMS, of course. So just keep that in mind when you do that prac, and think back to Michael's really nice talk this morning. So thanks again, Michael. So I'm delighted to be introducing Allison Love from Fertilis. Allison is the Chief Product Engineering Officer at Fertilis, where she leads all aspects of product development from manufacturing establishment to market release and production. Fertilis is improving IVF by precisely controlling the environment of the embryo using low-flow microfluidics and micromedical devices made possible with high-resolution additive manufacturing techniques. Allison joined Fertilis in 2021, bringing over 20 years of experience in product engineering and development, specialising in vitro diagnostics and delivering medical devices to market. Now, you've seen the presentation from Michael, which is from an academic's perspective, bringing things to our industry, and Fertilis is in fact doing something like that at the moment. You find out, I want a bit of a spoiler alert, so I don't want to tell everything, but meet and greet and talk to the team from Fertilis in the break. But Allison, you've got a wonderful perspective to bring to us from industry, looking at technology coming to the market, and we're really looking forward to hearing from you. Thank you.
Thank you very much. Good morning, everyone. I love engineering. I love how it helps to explain how the world works. I love how using that knowledge helps in how we sort of frame up the world, how we solve the problems. I love seeing an idea turn into a reality. I love seeing a prototype that becomes a product. It's really, really exciting industry to be part of. But I especially love how engineering can help change people's lives, how we can use it to advance cancer diagnostics, how we can improve the way that we test and diagnose and treat disease, and in this case, how we can help people have their baby. It's a fantastic industry to be part of. Understanding manufacturing technologies and how things are made is essential to translating good engineering into a product. I actually started in a double degree of mechanical engineering and industrial design, and I remember being in a class and they said, just focus on the design, don't worry how it's made. I worry how it's made. It's really important. I focused on engineering, and I was fortunate enough to participate in Formula SAE. So this is a race car competition for uni students. You get to design, but importantly build and then compete in your own race car. I did it for 2 years. They took us engineering students and sent us off to TAFE. We learnt machining and welding. Let me tell you, there is no better way to learn about the importance of manufacturing than having to make your own designs. And then redesign it, and then remake it, and then try again until something sticks. It's a really fabulous way to understand the interlinking of manufacturing and engineering. Learning machining and welding at TAFE, and later a role at Varian where they had on-site manufacturing, was fantastic. Really got to understand how you evolve your designs for manufacturing, but how understanding the different ways that things are made, how that evolves your design and makes that overall design better. 3D printing really changes the game in terms of manufacturing technologies. One of the first parts that I saw in terms of 3D printing was a shifter. So it was a print-in-place adjustable wrench. Fantastic. It changed the way that you thought about how things were made. So much so, this is a picture of my Prusa. My husband and I gifted it to each other for our 10th wedding anniversary. Very romantic, but love it. It's a really great way to keep sort of trying out new skills and really understanding what you can do. Medical devices often have a fluidic component. This is a Polaris 3. It's a tissue processor. This is bulk reagents and bulk fluidics, but nevertheless, precision is really important if you want to get a diagnostic outcome for cancer patients. At Invitech, we worked on more microfluidics. So we worked on a sample preparation instrument which took aliquots of blood, mixed it with reagent for HIV testing. We also worked on a blood clotting instrument which took a PDMS cartridge, you had a sample of blood, and then you looked for clotting. And having something that was in the operating theatre that allowed the surgeon to assess the clotting of the blood, again, really important to be responsive in that situation. So I was really excited to join Fertilis and combine my love of medical devices, combine my love of advanced manufacturing and microfluidics. Fertilis's mission is to help people have their baby. Infertility is a really big problem. In Australia, 1 in 6 couples will have issues with fertility. IVF is the treatment. And whilst IVF is amazing, its success rates aren't that good. 1 in 5 couples will get a baby out of an IVF cycle. It's pretty low odds. The Fertilis co-founder and chief scientific officer, Jeremy Thompson, had an idea 30-odd years ago about how he wanted to change IVF. By delivering culture media with precision to the embryo in the incubation environment, he felt that we could really change
Recording stopped.
Could really change the way that IVF was done and improve success rates so that people could have their baby. The emergence of 2PP, or two-photon polymerization printing, has enabled this. So what are the challenges with traditional IVF? On the top left is a jerry dish. This is actually part of my older product portfolio, so no shade. But this is a traditional dish. It is state-of-the-art in terms of it's used in a time-lapse incubator. And so what we see is a circular array of essentially microwells. These microwells can be thought of like a mini Petri dish within a Petri dish. The embryo is placed into each of these microwells, and what that allows for is for imaging. So as the embryo develops, the embryologist can see how the embryo is developing through those critical stages. What it does is allow the embryologist to decide at the end which are the better embryos, which one should be transferred. What it doesn't do is improve the embryos that are made. This is because the system is static. So at the start of an embryo culture, media is placed within the dish, the embryos are put into the incubator. 5 days later, we retrieve the embryos. It's kind of like putting out a buffet on a Monday and then still eating that Friday. Not the best. So why haven't they started to adopt microfluidics? Typical microfluidics for cell biology is PDMS chips. Very widely used. Certainly at Invitech we used it at several different applications. One of the easy ones was for PCR testing. So thanks to COVID, I think people are fairly familiar with PCR testing. But PCR is essentially your in vitro diagnostics. You take a sample, you run a protocol, you get a test outcome. It's the test result that matters, not the sample. So at the end of the test, the sample, together with a cartridge, is disposed of. Nobody cares about the sample, nobody's asking for their nasal swab back at the end of their PCR. So PDMS is highly suitable for in vitro diagnostics. Not so for IVF. For IVF, it's a sample that matters. We want the embryo at the end. PDMS doesn't really lend itself to that. It doesn't have the precision in terms of the geometry to allow us to collect the sample at the end and collect it successfully. The other issue with PDMS as it relates to IVF is that it's water permeable. So it will start to absorb water from the media. For IVF, what this does is it changes the osmolality of the media.
Recording in progress.
And in changing the osmolality, it changes the concentration, which can in turn kill the embryo. So really not suitable. Two-photon polymerization 3D printing solves these challenges. So what's 2PP? It's based on two-photon absorption, 2PA. Essentially what this is a nonlinear optical process, and what it does is it reduces the amount that is polymerized by the laser. So we use photosensitive material and a laser, and what that does is polymerize right at the focal point. So unlike one photon, 2PA gives us really, really small nano building blocks, which we can then use to build up a very precise structure from. There are two types of printing modes, VAT mode, bottom-up mode. For simplicity, I'm going to describe VAT mode, which is shown here. So for those of you that have your own printer or are familiar with filament 3D printing, it's conceptually the same except upside down. So we print our part directly onto a substrate. The substrate is connected to the stage. It's an XY movement, so that allows us to print the full section of the layer. We have our Z objective, which is like our printer head, which moves up and down, allowing us to print layer by layer the different part. Unlike with filament printing, where you're depositing the material, in 2PP, what you're doing is you're polymerizing the material. So you have a vat of resin. So what are some of the design considerations when 2PP printing? For starters, adherence to the substrate is really important. If you don't get good adherence to the substrate, you end up with a mess, and a mess that you need to clean out of the vat. If you adhere too well, then you have issues with collecting your part at the end. Design geometry and printing orientation is really critical. Just like with filament printing, you need to be able to build up your layers and they need to anchor to each other, which then anchors to the substrate. Overhangs are not possible. And unlike filament printing, where you can build up a substructure and remove it afterwards, at this scale that's really not practical. So giving thought about how you design your part, how you orientate your part, and what surface you adhere to your substrate is really important. Lastly, when utilising 2PP for manufacturing and for production, time is money. And unlike traditional machining techniques where you're looking at removing the least amount of material, here you're looking at the least amount of material that you can use. This also comes down to the fine and coarse mode. So how precise does your geometry need to be? And so getting that balance right is what allows you to then scale up for production. UniSA and ANFF have acquired the fastest high-resolution 2PP printer in the world, the Nano One. This is the 15th in the world and it's the first in Australia. I was telling my in-laws the other day what an absolute privilege it is to have access to this technology. It is truly amazing. I've got a video just to demonstrate the basic operation of this, so I'll play that. So selecting an objective, placing it into the machine. The next step is to place the vat in position and then fill it with your selected material. The stage is inserted. And then our substrate is that small glass piece in the middle that's positioned on the stage. It comes with software that allows you to set up your print. And then we can see the part being retrieved from the bottom here. The Nano one is fast. With up to 100 times higher throughput for production cycles, it supports scan speeds of up to 1,000 millimetres per second and throughput rates of 450 cubic millimetres per hour, which enables prototyping as well as production. It is not just the fastest in the market, it is fastest by far. So it can print in 5.5 minutes what a competitor technology can print in 163 minutes. That's pretty impressive. The Nano one comes with a range of different objectives, which allows for a range of different print sizes, as well as the fine mode and the coarse mode. So we can print all the way down to 200 nanometres range, all the way up to mesoscale parts. The laser wavelength is also compatible with cells, which enables biological printing approaches too. There are several materials that it supports, and importantly for us, there are 2 biocompatible resins. And it comes with proprietary software that's similar to any other sort of 3D printer, allows you to set up your part and your printing parameters.
Recording stopped.
Just ignore it, it's fine. Sorry.
No, it's fine.
It's not affecting those mine.
So how is Fertilis harnessing this technology in microIVF? We've essentially built a microfluidic system for the embryo. In the first instance, we've created a cradle for the embryo. Printed on the Nano one, this allows for easy retrieval of the embryo, rather than using a pipette, which can cause stress. It's similar to a baby capsule that allows you to move from the car to the stroller or to inside without actually disturbing the baby. The cradle is 300 microns wide, 300 microns high, and less than 1 millimetre long. I still have trouble getting my head around the scale of this part. It is tiny. I see it on CAD and it's this big, but seeing it under a microscope is genuinely amazing. The cradles are sized to suit a blastocyst, so that as the embryo grows, it can fit within this cradle before it's then transferred. We can see here that we've got a fin that allows the embryologist to manipulate the cradle with a set of tweezers. Through here we have access for an ICSI channel, and what that allows us to do is to perform ICSI where an egg is injected with a sperm. Lastly, and I'll talk about shortly, we have a barb here. The cradle then sits in the nest, and we're able to perfuse through culture media through to the embryo. Thank you, I'll be quick. This complex and precise geometry is not possible with any other manufacturing technique. I'll quickly run through printing specifications. So the cradles were printed in vat mode using a 20 times objective, a water immersion medium, and transparent low fluorescent resin up-opto. Was using a laser power setting of approximately 150 milliwatts, and coarse printing mode was enabled. We were able to print an array of 196 parts in 7 hours and 53 minutes, so 2.5 minutes per part. Cradles were post-processed and developed by sequential immersion in 3 consecutive isopropanol baths and cured using a UV light. They were washed in an ethanol and detergent solution so that they were suitable for use with embryos and non-toxic. Just run a quick video showing our resident embryologist removing the cradle and then placing it back in. There's also an interlocking feature which holds the cradle in place, again at an incredible scale. This is easily my favourite part. This has to be the world's smallest microfluidic barb, 90 microns in diameter with a 30 micron nozzle. The smallest microfluidics I've worked with is 1/16 inch, so 1.6 millimetres. Stand out, this is pretty good. We ran computational fluid dynamics simulation to work out how the flow would go through the nozzle and then fill the cavity. What we were looking for was how the distribution of flow would work. We printed these parts on the Nano 1 and were able to test for fitment, so how it interlocks and holds in place. And then we were also able to run a polystyrene bead to have a look at the flow. Amassing images, we were able to generate this. We were pretty happy with the alignment of what we saw experimentally with what we achieved through CFD. And from an applications point of view, this is really important. What we're able to do here is make sure that the embryo is evenly perfused. We're also able to substantially slow the velocity of flow, and that ensures that there's very little shear stress that's being applied to the embryo, which is important. Further, by using the Nano 1 for 2pp, it's enabled us to deliver flow rates as low as 600 nanolitres per minute to the embryo. This is our nest. It has an inlet, an outlet, a central chamber, and then we have an array of 10 50 micron channels. What this allows us to do is take very low flow rate that's coming in and then ratio and divide it. This system is under flow. For reference, this is a 1.3 millimetre ID tubing. We're using a red dye to visualise the flow through the channels. And we can see here the flow coming through here, but the cradles are all securely interlocked into position. We can also see the level of control that we get out of this system. So here we're perfusing and we turn off the pump. We can see the embryos move to the left. We then subsequently turn the pump back on and we can see the embryos again shift to the right. Few specs on the nest. So the nest was printed in bat mode again, but this time with a 10 times objective and an air immersion medium. We were using UpNano's high-performance polymer UpPhoto and laser power setting ranges between 50 and 100 milliwatts. Adaptive resolution printing mode was used, which achieved 4 hours and 31 minutes for one complete fully cured part. As with the cradles, the nest was post-processed in sequential immersion of 3 consecutive isopropanol bars. In addition, though, we were flushing each of the channels with isopropanol with a pump up to 3 bar. This level of precision has only been made possible by the use of 2pp. These were just a few applications of 2pp for microIVF and how Fertilis is using it to precisely control the environment of the embryo. It is really genuinely exciting to think about how we can use 2pp in other applications, from stem cells, gene therapy to drug discovery. The possibility to reimagine microdevices and microfluidics are almost limitless with this technology. And it's super exciting that this technology has come to Australia so that researchers, industry and our next generation of engineers can access this and see its full potential. This can be the crucible for the next innovations that improve people's lives.
Really amazing work that you're doing there at Fertilis. Exquisitely precise and hopefully inspiring a few ideas around the room what we can do with this new TPP capability here at ANFF SA. I would like to invite questions of Allison. Any questions? There's always a question, it's just whether it gets asked. All right, I'll ask a question. So what about your journey? I'm really interested to know. So it's 20 years of experience we're talking about, and you find yourself at Fertilis, which is a company that's growing very quickly, and it's great opportunities, wonderful technology. So can you say something about and you're in Australia, which is the other thing I wanted to say, and also Michael's presentation, a lot of the researchers that were showcased a bit there were Australian researchers. So could you say something about microengineering in Australia and your journey, and just, I guess, share a bit of that?
Yeah, absolutely. I think it's really exciting. The amount of work that we do in the medical device space in Australia is fantastic. There are lots of hubs that are specialising in IVD or in microfluidics. And I think having like the microengineering set up here is phenomenal. Like, it's really exciting. Certainly compared to, many, many years back what we had at uni. The kind of access is fantastic. And it really supports innovation, and it really supports being able to rethink how we do things, so that rather than just sort of applying old techniques and old processes, we can really reconsider how these applications need to be solved.
That's great. Any questions inspired from the group? There must be one. Michael, please.
If no one else has got one, I've got one, Craig.
Break the ice, Michael.
So Allison, thank you for your talk. That was really amazing. One of the criticisms I've always seen about 3D printing additive manufacturing is that you can never manufacture at scale because it's just not cost competitive. That's not the way you're thinking. So you're planning to manufacture with the two-photon polymerization, right?
We absolutely are.
And that is cost and time competitive with all of the other approaches that you could possibly use?
Absolutely is. So what we're looking at is how we integrate it with other technologies. So we're not intending to print the entire dish out of 2PP, but we're trying to make the most out of what 2PP offers for the features that we need, and how that complements other technologies like injection molding, those sorts of things. But yes, we are absolutely going to production with 2PP.
Awesome. That's a good
Yeah,
question,
it's exciting.
Michael, and a really exciting answer.
Recording in progress.
I don't know what's going on. We'll sort that out in the break.
I too, right here.
I've got a whole team working on that, so it's not just me, Michael. It's not just me. Look, I just want to say that most of you will be familiar with 3D printing at larger scales, and the sites with widgets and things you'll see in a lab tour, where somebody said, we printed this and we couldn't make it before. Right? This is a new device or a new structure that could not be fabricated and manufactured before. We're now talking at exquisitely small scales, being able to do those same impossible fabrication steps, moving parts, etc. at very, very small scales. And that should be exciting to every single person in this room. So think about your ideas. The capability is right here on campus. It's open access. You don't have to buy your own very expensive printer. You can get in there and use it yourself in your projects or your research or your studies. So
Recording stopped.
So think about that, and go on tour and enjoy seeing the capabilities, and just imagine, because it's that imagination 30 years ago for Jeremy and the team that's realising industry, startups and commercialisation, and helping people in the process. So engineering has a very big part in rescuing us from some of the big issues facing the globe. So think about your ideas, talk about them over morning tea, but before you go anywhere, please thank Allison again. Okay. Welcome back from morning tea. I'm looking at the room, and this half of the room is back and well fed and everything. This half's a bit light. I don't know where the others are. They're still getting their coffees or eating their morning tea. But good to see you back. I'd like to thank our sponsors. EVG is the first sponsor. Here's a quick video.
Recording in progress.
Amazing technology. Yeah. You want to buy a car? Let's go. So a big thanks to EVG for supporting the Winter School and also producing amazing technology that we have in our facility here. So you'll get your hands on some EVG gear. The same is true for Olympus, which we'll show you right now.
The DSX-1000 all-in-one digital microscope is the tool of choice for inspection and failure analysis. With speed, flexibility, guaranteed accuracy and repeatability, and high-performance imaging software, you can be confident in your results. The DSX-1000 system has features that enhance the speed and efficiency of your workflow. Instead of having to use one optical microscope to conduct an initial low magnification inspection and a second for high magnification detailed analysis, the DSX-1000 enables you to do both on the same system. And unlike some digital microscopes that require time-intensive lens changes to switch magnification, the DSX-1000 system's quick-change lenses enable you to complete your inspection fast. 3 key values for workflow innovation. During analysis, the system's suite of advanced features enable it to excel in many applications. A magnification range from 20 times to 7,000 times enables you to view a wide area before zooming down to the micron level for detailed analysis. A range of lenses is available, including for high resolution and long working distance, while the rotating observation head and stage let you view your sample from almost any angle. Multiple observation methods are also supported. The best image function enables you to view your sample under 6 observation methods on one screen. So you can quickly choose the one that works best. And all magnifications are available in every observation method. High-resolution 3D images are also possible, with speeds up to 10 times faster than the previous DSX model. Unlike some digital microscopes, the DSX-1000 system's measurement accuracy and repeatability are guaranteed, so you can be confident in your results. The telecentric optical system corrects for the convergence effect that can make the size of an object look different depending on the focal point, greatly increasing measurement precision. These features are just a fraction of what the DSX-1000 digital microscope can do. The DSX-1000 incorporates a variety of functions to support analysis tasks. In pursuit of ease of use, speed, and accuracy, the DSX-1000 all-in-one digital microscope contributes to the reduction of analysis time and workspace. To learn more, please visit us at www.olympus-ims.com or contact your local sales representative.
Oops. Okay, so a big thank you to our sponsors. Just going back to, where is it? Yes, a big thank you to our sponsors. Without them, this winter school wouldn't be possible, but also you wouldn't have those amazing people in the foyer to be chat over coffee and muffins and things. So thank you to them. All right, well, we're going to move to our next lecture, which is going to be on etching. Now, etching is really very important. It's ubiquitous, really, in fabrication. We've talked already about coating, putting down thin films, which could be sacrificial layers or they could be electrodes. We've also talked about patterning to be able to create the structures and arrays that we need. And in this talk, we'll now show what we can do once we have those patterns or coatings as masks, usually, to be able to do some structuring. Not just changing the chemistry, but now doing the structuring to get the devices that you want. And so Dr. Donghoon Chang is part of our ANFF SA team. It's great to have you speaking again to us today. I saw here that it reminded me that you joined us in 2014, Donghoon. You're a long-standing member of the team, and curiously enough, that was the first year of the winter school. So Donghoon hasn't been able to escape winter school for his entire time with us. But Donghoon, thank you for preparing this presentation on etching. He completed his PhD at the University of Adelaide, which focused on the development of analytical and numerical tools for predicting fatigue, lifetime of structure components having mutually interacting cracks. Before his PhD, Donghoon worked at Samsung Electronics as a senior process development engineer in the field of micro electromechanical systems, MEMS, and microfabricating optoelectronic devices, including vertical cavity laser diodes, PIN photodiodes, and micro machining silicon optical benches. So you can see that we have some amazing skills that have come into the facility and are at your disposal. So get to know Donghoon, ask him all your tricky questions about fabrication and life at Samsung, and what his last 9 years working with us has been like. 10 years next year, Donghoon. So please welcome Donghoon.
Thank you, Craig, for the nice introduction. How much time do I have, Belle?
I'll try for
Okay. Yes, good morning to all of you. Thanks for attending this presentation. I'm very excited to talk about this interesting technique used in the fabrication, micro-nano fabrication. Yesterday we learned about thin film deposition techniques in Colin Hall's lecture. Also we learned about lithography technique by Miriam. And then I would say these three techniques, thin film deposition, lithography, etching, are three pillars supporting micro and nano fabrication. Why etching is so important? Etching and lithography techniques, they dictate the feature size, the scale of your devices. Also, it dictates the density of devices in a limited area. So, sorry. Next, and I'm going to use this pointer. Yeah, today I'm going to mainly talk about reactive ion etching technique, given that I have limited time. And then I'm going to start with these simple questions about etching. What is etching and why etching is important? Why etching is widely used in micro-nano fabrication? First thing, etching can be defined as a pattern transfer process by selective material removal through pattern etch mask. Let me use these drawings here. This drawing highlights three steps used in pattern transfer by etching. In the first step, etch mask material is deposited onto your etch target substrate and then patterned like this. But in the first step, the protected area and non-protected area in the subsequent etching process are defined. In the etching step, obviously, this patterned substrate having etch mask pattern, etch mask layer, is submerged into an etching environment, and this etchant selectively attacks this etch target material, hopefully without damaging this etch mask pattern. And then in the last step, we just do not need this etch mask pattern anymore. And then finally this etch mask is stripped off and removed, and then recover the original surface of the substrate for subsequent fabrication steps. And this material removal in etching can be a chemical process or sometimes ion-assisted chemical process. Let's not worry about this ion-assisted chemical process at this stage. We're going to talk more later about this. Then why etching is so popular in micro nanofabrication? I would like to suggest two answers here. First one is etching is substantially a non-contact material removal process. That means you do not need to worry about frictional heating caused from contact between workpiece and then tool. Also, you do not need to worry about the deformation of your workpiece. All of these can produce these highly accurate and very high resolution features through an etching process. Another beauty of etching is that it's a wafer level process where material removal occurs all over the wafer level. And also this wafer level process can be easily extended to this batch process, right? So through an etching process, through a very nicely developed etching process, you can achieve very high uniformity and repeatability in etched structures. Also, etching can be a very fast and cost-effective option for microfabrication. This slide highlights some interesting features, geometries you can achieve through use of etching techniques. And the first one is shows a comb drive. You can see a very vertical and high aspect ratio structures formed on a silicon wafer. And then this can be used as an actuator and sensors in a MEMS devices. The second image shows an array of micro needles for drug and then vaccine delivery patches. And third one shows a micro lens arrays for micro optical systems. And then fourth one shows a micro fluidic device containing micro channels for handling a tiny amount of liquid. As you see, etching can enable the fabrication of these interesting and then powerful functional devices. Of course, to make a very specific profiles of structures, you need to also combine etching technique with specially developed lithography technique as well. Okay, now we need to look at some theories and then underlying mechanisms in etching. And there are two etching mechanisms used in this process, in etching process. First one is a chemical etching mechanism. It's a very, we know, I think most of you are familiar with this chemical etching mechanism. Just chemical etching mechanism make use of reaction between etchant at the surface level, the spontaneous chemical reaction between etchant and then the surface material here. And then to make this surface reaction sustainable, we need to have a supply of this etchant at the surface. Also, you need to remove this etch product from the surface. These are three basic steps that must occur for a chemical process to proceed. And then physical etching mechanism is relevant to reactive ion etching. It involves the generation of ions in a plasma, and then acceleration of ions toward the target surface, and then breakage of atomic bond on the surface level, and then to remove material from the surface. So let's remember these two etching mechanisms, and then What are reactive ion etching? Let me keep it simple. These are two representative etching techniques used in micro nanofabrication. And the biggest difference is this etch profiles and then maximum aspect ratio you can achieve from these techniques. Isotropic wet etching will lead to these isotropic etch profiles like this, round etch profiles. And then you can see also this undercut under this etch mask. So there is always a shift between your etch mask and then etch structures you finally get at the end of the process. And then, but in reactive ion etching, aim is to control the etch rate and then increase the etch rate in vertical direction and then suppress etch rate in horizontal direction. By doing this, you can achieve these vertical etch profiles. We call that anisotropic etch profiles. Etch rates are different. And this is the biggest difference between wet etching and then reactive ion etching. Yeah, let's have a closer look at wet etching. And yeah, let me skip some part because I have limited time today. Wet etching used to be a dominant etching technique in IC manufacturing, and because of the simplicity and the economy of batch process. And we know that isotropic wet etching can lead to these isotropic wet etch profiles. Because of that, because of the dimensional shift between etch mask and then the final etched pattern, it has limited capability in achieving high resolution features. That's one critical limitation. Another limitation is the highest aspect ratio. Highest aspect ratio you can achieve from wet etching is 1 to 2. That means when you etch a trench structure with the width of the trench, if the width of the trench is 2 micron, then the maximum depth of trench is 1 micron. You can go higher than that. That's the maximum aspect ratio you can achieve from this isotropic process. And this shows the wet etching profile. This SEM image that shows the isotropic wet etch profiles formed on a borosilicate substrate by using hydrofluoric acid. This is isotropic etchant, and then chromium gold as etch mask layer. As you see, the etch front in wet etching, isotropic wet etching, etch front proceed as a spherical wave, so etch rates are equal in all directions, horizontal and vertical direction. And then that's the reason we end up having these round etch profiles. And then aspect ratio is, maximum aspect ratio is 1 to 2, I would say. This wet etching can be sometimes anisotropic. It's a very interesting topic. And then if this silicon crystal plane anisotropy, wet etching of crystalline silicon can be anisotropic, I would say. And then if this silicon crystal plane anisotropy is used, then what is this crystal plane anisotropy? It's more specifically, it's a crystal plane atomic density anisotropy. Right. This diagram shows a unicell of diamond cubic crystal structure. We can see 3 equivalent crystal planes. This is 100 plane in blue, and the 110 plane in red, and then 111 plane in green. These 3 planes, equivalent planes, show different atomic packing density. Can you see that? And then packing density are different on on different planes. This can lead to a different etch rate in a certain type of etchant. If the etchant is correctly selected, then etchant will selectively attack certain planes without, with minimum damage on other planes. That's that's the underlying mechanism of achieving anisotropic etch profiles on a crystalline silicon structure. And then, for example, atomic packing density, 111 planes shows the biggest atomic packing density. That means it shows lowest etch rate in certain etchant. And then, so for example, in potassium hydroxide solution, and the etch rate of 100 plane is 200 times higher than etch rate of 111 plane. Yep. And then the next slide shows this anisotropic etch profiles formed on 100 surface orientation wafer. This is like inverse pyramid shaped etch pit structure. And the other one is formed on 110 surface orientation silicon wafer. And the vertical, we can see these vertical trenches by using wet etching technique. And in both cases, I would like to get your attention that the side walls are formed by 111 planes. That's because etch rate of 111 planes is extremely low in a KOH in a certain solution. And then that plane acts as a etch stop planes. Now it's time to move on to reactive ion etching. Reactive ion etching basically combine chemical etching mechanism with physical etching mechanism. And this is a currently dominant etching technique used in IC manufacturing. This technique is this technique dictates the density of devices and then critical dimension of devices, I should say. And because of this directional etching capability, there is a minimum dimensional shift between etch mask and then etched features. You can achieve these high resolution features. Also, you can achieve high aspect ratio features. Right? You can make very narrow and very deep cavities by using this directional etching technique. This item highlights RF plasma discharge mechanism. When a process gas mixture is supplied into this RF biased chamber under a vacuum, these gas molecules collide with high energy electrons accelerated in this field, and then some of them are ionized, and then some of them are dissociated into smaller molecules. This mixture of ions and dissociated molecules and electrons are referred to as plasma. We make use of this plasma in reactive ion etching. In sputtering process, we also learned about plasma, I believe. But that's a different plasma, I would say. Let me explain that further in this slide. This slide highlights the electron atom or electron molecule collision process. There are various collision processes like this in excitation. And the high energy electron provides energy to this atom, and then this bound electron is excited and then jumps up to this high energy level. And this excited state is very unstable, and then this electron returns to this ground state, and during this transition, photon is emitted, and then this energy of this photon corresponds to this energy band gap here. In ionization, energy provided by this high energy electron to this atom is larger than the ionization voltage of this atom, and then that can cause this ejection of this electron in the outermost shell, and then turns this previously neutral atom into ions, positive ions. And in dissociation, this big gas molecule is broken into smaller molecules if the energy of this electron is larger than the binding energy of this molecule. And after this, we can see the smaller dissociated molecules. And then have got this dot. That means they are, after dissociation, the smaller molecules are extremely reactive. They are called radicals because they are chemically very unstable. So when you're generating plasma for reactive ion etching, these two, ionization and dissociations, are very important. You need to generate ions and then dissociated molecules. Dissociated molecules will remove material, your target material, chemically, and then these ions will enhance the chemical reaction. That's called ion-assisted chemical reaction. But in sputtering process, in just argon sputtering, physical sputtering process, you do not need these dissociated molecules, right? You just need these ions. And this is a physical sputtering process in your plasma. Aim is to generate just ions. You do not need other dissociated molecules there. You just need, and also in chemical deposition process, for example, plasma enhanced chemical CVD process, it's also a bit different. And then you need this. You don't not in that PCVD plasma enhanced CVD process. You do not need these ions. You just need dissociated molecules. And then after reaction, difference is after reaction in dry etching process, reactive ion etching process, after reaction, these dissociated molecules or radicals should generate etch product which are volatile, having high vaporization pressure. Otherwise, it's going to be difficult to remove this etch product, and then that etch product will slow down the etching process. But in PCVD process, for example, this etch product should not be volatile. It should be involatile because you are actually collecting the etch product in your PCVD process. Right? So plasma is used in sputtering, used in reactive ion etching, used in CVD process, but it's a bit different. Aim is a bit different depending on your use of plasma. In reactive ion etching, there are two approaches to enhance etch rate in vertical direction. The first approach is the use of this ion-assist chemical reaction. These directed ions, right? After generating ions in your plasma, we direct them toward this your target surface, and then these ions will collide with the target surface in the vertical direction.
Recording stopped.
Yeah, vertical direction, and then this sidewalls is not going to be bombarded with this ion irradiation. Only this horizontal plane will be irradiated with these vertically directed ions. Then what's going to happen? Only this horizontal surface, etch rate on this horizontal surface will be enhanced, right, through the chemical reaction. So this ion bombardment it just enhance the chemical reaction in vertical direction. Right? That's the ion-assisted chemical reaction. By using this process, we can improve the etch rate in vertical direction, and then without, causing etching inside or on sidewalls. Right? That's one way of implementing vertical and sidewalls in anisotropy in dry etching, reactive ion etching. And another way is passivation of sidewalls. This ion-assisted chemical reaction may or may not occur depending on the combination of your plasma chemistry and etch target material. Right? If you see that ion-assisted chemical reaction, that's simple. You just rely on that process. If that ion-assisted chemical reaction does not happen, then you need to think about using this sidewall passivation technique. I'm going to talk more about this technique in deep reactive ion etching process. And then, yeah, thanks. Well, reactive ion etching, theoretically, we can control the degree of anisotropy by controlling process pressure and ion energy. For example, just one example, if you increase this the process chamber pressure, then that means you're going to have more reactive species in your etching environment. That will lead to increased chemical etching, which is kind of isotropic, which produce isotropic profile like this. And then on the other hand, if you increase ion energy, then ions will bombard your target surface with a higher kinetic energy, and then that can increase this isotropy on your profile. This image shows some etched profiles by reactive ion etching, and then we can see very vertical etch profiles. Okay, now let me talk a little bit about deep reactive ion etching. This is a second implementation to achieve that vertical sidewall profiles. It's about sidewall passivation technique. And in this process, the first step, we can see this etch mask pattern, and then this technique uses fluorine as etchant, because fluorine gives very high etch rate. But the problem with fluorine is that the etch profile is partially anisotropic. So you can't keep going with fluorine, with chemical reaction with fluorine. If you keep going, you will end up getting this round etch profile. It's more like, it's not completely isotropic, it's not, but it's partially anisotropic profile. It's not desirable. So to overcome this problem, in the second step, we introduce a passivation layer, which is coating of, which consists of coating by C4F8 gas, fluorocarbon gas, and then in this, after this patching step, in the next etching step, this fluorocarbon protective layer on this horizontal surface is removed because of the vertically directed ion bombardment, and then this coating on the sidewall and it remains intact. So after removing this coating, another silicone etching proceed. By repeating this etching and passivation step, you can achieve globally vertical etch profiles. This same image shows a series of cavities formed on a silicon wafer by a deep reactive ion etching process. We can see cavities having different opening and then different depth here. All these cavities were formed on a single wafer at the same time in one process. Then what does this shows? Firstly, I would like to highlight that the deep reactive ion etching's capability in achieving high aspect ratio structures. We can see these very narrow and deep cavity structures, which is not possible with isotropic wet etching process. And then aspect ratio of 50:1 is known to be possible by using a deep reactive ion etching process. Also, this SEM image highlights this phenomena called aspect ratio dependent etch rate. As you can see here, wide openings, cavities having wide openings has got deeper cavity. That means aspect ratio, depending on the aspect ratio, etch rates are different. And then with these high aspect ratios, the etch rate is lower. Then what's the reason? Then chemical species and then accelerated ions, they find it more difficult to reach the bottom of this narrow and then deep cavities. Yeah, also we can see these scallops, undulation formed on this sidewall, and then that's kind of inevitable in deep reactive ion etching process because we have to use this etching and then passivation steps. This one scallop corresponds to one cycle of etching and then passivation step. Okay, that's all I think I'd like to talk about. Thanks for your attention.
Well done, Bill. Bell was just about to tell Donghoon he's close to the end, and he did a beautiful job with the questions. So any questions for Donghoon about etching? Come on. Yes, here we go.
Yeah. Is the chemical ion process ever done without photolithographic masking?
Without?
Without. So is masking always applicable?
Yes. I said it's etching is a selective material removal process. It's through a use of etch mask pattern. So when you're selecting etch mask pattern, and then you need to think about the selectivity. Then the chemical, you don't want the etch mask to be damaged in the etching environment. So you should carefully select etch mask material so that the damage is minimum in the etching process. And also, removal of etch mask very critical. You have wonderful etch mask, very good select, has a very good select, very strong in the etching environment, but it's also very difficult to remove. Then it's going to cause pain for the next fabrication process. It's very important to recover the original surface. It's microfabrication. It includes multiple steps. Etching is not the final step, and after etching, another metallization, more etching, or some more diffusion, or other process. For that, recovery of the original surface is very important. So you need to think about that when you are selecting etch mask material.
There might be a couple of special cases. You might actually want to make a roughened or structured surface like a frosting, so that could be a case where you want to expose the surface to roughen it deliberately through an etching process. It's a bit unusual for the context of what we're talking about here. But the other one might be a sacrificial layer. So at the end of a process, you might want to remove all the gold or all the whatever material you've put down before. So you might not pattern it, you might just chuck it in at that stage, remove everything off, and then continue to process your wafer. So there could be a couple of cases, but typically you wouldn't, you need some masking to create the structures that you'd like.
My question might actually be covered in the next lecture, which I see is on laser milling. So,
Mask free, yeah.
Okay.
Yeah, good point. Excellent. Good question. No questions online. Any other questions? I really want to encourage questions. That was a great question. Let's see if we can get one more. Somebody. Yes, please.
I'm a high school teacher, so the first thing is my students would ask me, what is this wonderful, amazing technology used for in the real world?
Good question. So I'm not sure if they can hear online. So that was what is this amazing, wonderful technology used for in the real world? Great question.
Yeah, the biggest market for etching, I would say, semiconductor industry. The etching is used for isolation of devices and then also interconnection of nano electronic devices. That's the biggest market. I didn't highlight that in my slide, and I just showed some small market applications like needles and lamps. And lamps is still a very small market compared to the semiconductor industry, but I would say without etching technique, we can't fabricate microelectronic, nano-electronic devices. It's critical technique for the realization of scaling devices.
So basically, no etching, no iPhone, no flat screen TV.
Metallization.
It's basically in everything, yeah. Okay, we might continue. Thanks very much, Donghoon.
There's one quick question.
Oh, okay.
Sorry, Donghoon, apologies, this has just come up. Between physical and chemical etching, which one is better for oxide-based materials?
Oxide-based material.
Which one is better?
There are many things to consider when you're choosing that between wet etching and reactive ion etching. And the dimension is critical. What dimension is required, and then what is the underlying material? There are so many things you need to consider. I can't choose that each one is best for oxide material.
Was it the whole screen?
Yeah, good to go, hey?
No, the whole screen. Just want this one.
Oh, just the PowerPoint.
That's
Yeah,
probably better.
no worries.
Okay.
All good.
All right. Well, I think I mentioned already that Ben's come all the way from the other side of the country to be with us from the East Coast.
Not from
But
Perth.
don't hold that against him. That's all right. So, Ben Johnston is, I should say, Dr. Ben Johnston, to introduce you properly, is a good friend of our facility. And in fact, a lot of the devices we make might spend some time in Ben's hands over in New South Wales at Macquarie Uni to be able to create some structures. And I won't spoil, won't share your
I've
thunder.
got a spread of stuff.
You're going to have amazing talk from Ben, but they will actually spend time with him to then come back, and we often do bonding and finishing of those devices here. And so let me do the official bit. Ben gained his Bachelor's of Technology in Optoelectronics in 2004 and a PhD in Physics from Macquarie University in 2008. Since 2002, Ben has assisted with the running of semi-commercial laser machining service offered by Macquarie University. These facilities and activities form part of the Australian National Fabrication Facility, in fact as part of the OptoFAB node, which you'll see tonight. Don't forget to register. And Ben's role is to provide fabrication services for researchers and industry using applied laser technologies. And dare I say, if there's anything about laser machining that Ben doesn't know, it's not worth knowing. So we're looking forward to hearing from you today, Ben. Thanks.
Thanks, Greg. That's a very tough rep to live up to, that one. As you'll see in this, it's such a diverse field and areas of such specialisation with what you're doing with the tools that I dare say there's some very good people out there doing stuff, and they keep it secret. There's a lot of know-how behind this sort of caper. So thanks, Craig. Yes, I've come down from Macquarie University. It's great to be back in Adelaide after a couple of years hiatus that we had because of COVID. And thanks very much to Belle and Craig and Simon for the opportunity to roll up again. So where I come up from, next slide, come on, go. There we go. It's going to be a bit slow. Okay, so about the OptoFAB node, hopefully most of you are signed up to go down to University of Adelaide this evening, where you'll see Heike and the team talk about some of what they do there. But the OptoFAB node is actually distributed across 4 of these universities at the moment. So we're a node within ANFF which has a thematic collection of stuff where we're either making devices that manipulate light or using light in fabrication. And that's where the laser machining I'm going to concentrate on today comes about. But this evening you'll see stuff down in Adelaide which is just on another level where they're refining various different glass chemistries, extruding optical fibres, as well as some very nice additive and subtractive manufacturing down there with a 3D printing. So I hope you get along. What's new in OptoFAB in the last couple of years is that we also have some glass 3D printing, which is a new tool at Adelaide. Hopefully Heike shows that off. That's a very interesting emerging area. They've also got some nice new Stratasys printers for doing composite plastic printing and things like that. So there's a real hive of activity down there. And then you'll also hopefully get a chance to catch up with Evan, who's the machinist there. I would encourage everyone who's come along this week to use the online materials that will be at your disposal to watch through Mark Sherrill's presentation, which he's devastated not to have to give this year, about the machining work that gets done here at UniSA. There's a sister facility also at University of Adelaide where Evan will show you the DMG mill there, where they can actually do freeform glass machining and some really good stuff. One of the new activities we're very excited to have on board is the resumption of precision optics manufacturing in Australia, and that's been looked after mostly down at ANU by Steve Madden. He is recommissioning some of the tools that were under CSI Rowe's remit for many years. They're the sort of tools that built the mirrors for LIGO, the gravity wave interferometers. But Steve's also taking on additional tooling in collaboration with DSTG to do some interesting freeform optics and things like that as well. ANU will be opening a new fab similar to what UniSA has done here down at ANU in the coming weeks. So that's a very exciting development. And then we also have a small contribution from our mates at University Technology Sydney, where they've come on board to offer to ANFF the ability to manufacture and move around some very special optical materials like monolayer HBN, which is a very hot material for quantum optics, as well as diamond optical materials. And UTS is also developing a little fab down there, which has a niche in some challenging etching and deposition tasks, which usually aren't taken on by other people, such as ion beam sputtering and chlorine-based chemistries. So some fairly nasty etch chemistries that not all fabs want. UTS has put their hand up to take that on. So the OptoFAB node is a very busy activity, and it keeps me on my toes. So onto the laser machining. So laser machining, this is my little baby. I think, like Colin said the other day, he's been in thin film deposition for a couple of decades and it's kept him busy. I'm starting to get the same with the laser stuff. I've been doing this since that 2002, once I first stepped in the lab at Macquarie University during my bachelor's. Very simple process in principle. You need some lasers and optics. Now, I'm not going to talk about laser development and stuff too much. Essentially, you're buying an OEM laser off the shelf. But there are dozens of different types of lasers, and that's hopefully what I can impress with you in the next couple of slides. And you need the horse for the course, and there's so much available now, it can be a very daunting area to get into. Coupled with your laser, you need some very precise motion and beam scanning. Okay, you want to fabricate stuff on micron scale or with micron tolerances. You need your hardware to be very good. So there's a whole other area of science in motion control. The company that I'm showing here, which we largely stick with, is called Aerotech. They're an excellent motion control company, but there are several others as well. So you usually need to pair these things together, a laser company, a motion control company. And then there will be some other gases and chemicals that assist the process depending on what you're doing. So they're the basic ingredients. But in regards as to the common types of lasers you'll see around in your workshops and things like that, everyone probably is familiar with seeing a CO2 laser work, okay? These are lasers which, and I have an example here from quite a nice CO2 laser company, Trotec. These are essentially a 9 to 10 micron laser. The laser is essentially just a precision heat source when you're doing this sort of cutting, okay? These lasers, you can buy them off eBay now for about $500 for your garage if you want to, right? CO2 lasers are really common. They're really cheap. The thing, though, is that they're not really suited to the micro nanofabrication that we're talking about, but they can do some great stuff. Here it is just cutting up a sparkly piece of acrylic for a bit of signage. And that's where a lot of these gantry CO2 systems will sit around, will be in sign makers' workshops and things like that, okay? So when people say lasers, CO2 comes to mind, not really useful for what we want to do in micro nanofabrication, though they will remain nameless. We've had some students that have said, can I do this with a CO2 laser because it would be cheap? Okay, if you want to make 50 micron features of microfluidics with a CO2 laser, have fun with that one. The other type of laser that's really impressive to watch work are the kilowatt lasers, the slab lasers, the fiber lasers, which are used in heavy industry. These lasers are on a completely different level to what we're going to talk about as well. Again, they are using the laser as a precise heat source, but they are using kilowatts of average power, and they're using many bar of air blowing through the cut to blow the metal away. They're fantastic machines to see work. But the sort of fine features and things we're trying to make will actually either fit inside at least the kerf of these lasers, and the features that we're making would also be very easily blown away by the air assist on these systems, okay? So what I'm going to talk about is not going to be really applicable to either of these sort of industry standard areas that we're talking about. Another application for lasers, which will be topical for your visit tonight, but also we operate a similar system up at Macquarie, is the use of lasers for laser sintering and laser melting. People have seen the beautiful 3D printed metal which is available now, and largely these are made possible by laser-based technology. So the little clip I'm showing here is actually a fiber laser which is being galvo scanned from above, and that's welding a layer of powder together to build up a 3D print. And hopefully Lejesh and the guys at Adelaide can give you a bit better look at inside their machine this evening when you go along. So that's a bit of an overview of the lasers, but this is not really what I want to talk about when I'm talking about working at these fine tolerances on the sub-millimetre scale. So we're going to talk about an area called micromachining, and this is the little dimensional area that was drawn up many years ago where we talked about which nodes in ANFF work on which length scale. And of course, you know, down at MCN and also at Sydney University and other places,
they're working with electron beam lithography. They're working down at tens of nanometers. So they're right down there. Where the lasers and things fit is sort of in that gap between tens of microns and millimeters. It's an area of distance where it can be difficult to get things made at a conventional workshop with tooling. It's not quite small that we call it nano, but we're still looking at features which are sort of like 5 microns or so, even sub 5 microns when you're trying to be clever. So there'll be components which look like this. These are metal plates and dog bone structures, which are sort of on the centimetre scale. Then we get down to cutting little features, which are sort of on the millimetre, sub-millimetre scale. So what I have here are some little pieces of gold. These are resonators for radar electronics, so these are little pieces of gold we cut out. We also do little micro components. This is a bit of an old video now, but this is just showing a little propeller that we've laser cut from some 50 micron metal, and this is about 1 millimetre in size. So these are fairly tiny features, pretty hard to do, though Mark would lap it up on the mill these days. The mechanical machining of components like this is also quite readily available. But if you want to make dozens of these, laser cutting them can be pretty good because the tooling can wear out and be quite expensive. If you've got a nice laser that's working well for you, the photons are essentially free. Stepping down a little bit smaller, one of the things that we're regularly doing with our systems is cutting small holes and apertures for various applications. Whoops, I stepped forward one too many. That's probably okay. I'll just hit that go again. So these are just small apertures either for flow, okay, or for leak detecting. So one of the more mundane jobs I have in my role, and this comes up several times a year, is working with pharmaceutical companies that have to do quality assurance on their packaging. In order to do that, they have to demonstrate that their online leak detection systems will find holes which are 5 microns and smaller. And so we actually have a little run of work each year for these companies putting deliberately small holes in the packaging so that they can validate their leak detection. This is the sort of stuff that we get involved in. Okay. So what's it look like when we do our micromachining? I have a couple of videos here. One is a very old one, but I still play it because it's obnoxiously noisy. This is back where I started using copper vapor lasers to cut foils and things like this. And these were lasers which ran at about 6 kilohertz pulse. That's what you're hearing. It's a horrible pitch to stand around and work in all day. But essentially we're focusing a green pulse laser onto target with an objective, and away we go, we're cutting. There's no air assist. This is all done in fairly ambient conditions. This is back in the early days. These days we've been able to upgrade. The next system I have here is our current workhorse. We got this into the country in around 2012. Let me just jump the video ahead a touch. Oops. Go. What did I click on there? Play. Yep. Still going. All right. I will let that kick in, and now we should see some action. So these days we're using a more sophisticated setup. DSTG like this so much that Igor got one of these toys as well, sitting out at Edinburgh and Adelaide. So there's a few of these floating around now. What we're doing these days, we're using more advanced laser sources, so we're going to shorter and shorter pulse energy, and I'll describe in a moment why that is. But the systems themselves are much more sophisticated looking. They are really pretty sophisticated CNC machines here. What you're seeing happen here is we're combining two different motion systems. We have the XY table down the bottom with the silicon wafer vacuumed onto it, but then we also have the galvo scanning, which are fast mirrors which are actually scanning the beam around. So these are the sort of combinations of CNC bits and pieces you put into these laser machines. And right at the end, hopefully I have some time to show you some videos about where some of the companies that are at sort of the leading edge of this, where they're going with their automation. It's really quite impressive what people are getting to. So this is sort of a look at the machine that we run day to day these days and how it works. What's running there is just laser marking of a silicon wafer. We do get into processes which are a little bit more advanced like that, but this is a nice demonstration we have of the system working. Okay. So where is this field? This is a really difficult field because it's really diverse. There are so many people looking at different laser sources and different processes and honing in on it. A lot of the stuff that ends up being industrialized is driven by the mobile phone and the display screen industry, whether it's cutting the glass for the display panels or marking the ITO layers to define all the electrode buses and things like that. There is a whole wealth of niches. This is just an example of the literature you can come up against, okay? Dieter's book is very good, but it's about 450 pages to get through. It is segmented into areas where you can concentrate on ultra-fast laser processing and things like that. And then there are many, many of these compendiums of papers and workshop articles on certain fields of the area. So here we've got, femtosecond laser machining in transparent materials, general laser processing of materials. It's a really busy field to get into, and if you go Googling for a particular process, you'll soon find yourself very confused and very vague on really what's going on. So having a bit of an experience in this area does go a long way, and hopefully we're a reasonably good resource within ANFF to help people out with this. The reason for this is there's a lot of stuff that goes on here, right? The material that you're trying to process has to absorb the laser, and then a few different things can happen. It can either just heat up, it can start melting, you can get evaporation, you can start to displace some of the molten material. Sometimes you can decompose the material, especially with polymers. When you're machining polymers with UV lasers, you can start to decompose the material. You can get some more energetic processes happen, and that's what I've got there, phase explosion, okay? That's a really exotic process where the material is going from the solid to the gaseous phase almost instantaneous, and the whole area, because you're looking at a massive expansion in volume, the whole area that's been irradiated explodes. That's not necessarily what you want to happen all the time. Some of the more exotic stuff that happens is the last one I have there on the list, which is coulombic explosion. And this is something that's specific to ultra-fast laser processing, where you will actually exceed the work function of the material, strip out a whole population of electrons from it, leaving you with a positively charged plasma, which will then expel itself away from the surface, without putting a lot more thermal load into the material. And that's the sort of regime we want to be in. To control what process dominates and takes place, you have all these different handles that you need to have a handle on with your laser. The wavelength you're using is important because it determines how the absorption proceeds, whether it's linear or non-linear or multi-photon. You also have to be concerned with the pulse repetition frequency of the laser so you don't get too many cumulative effects. Sometimes you may want cumulative effects. The pulse energy, how hard you're hitting it with each pulse, the spot size that you're getting from your laser, but then also the CNC machine you're running to get the part that you want. It can be a very busy area to get on top of, and this is where I've spent a lot of my time developing these sort of blind recipes to try and do things well. And it can look pretty nasty sometimes. It's all about managing these processes. These are some examples of some pretty suboptimal machining. The picture that I have in the middle is a silhouette of the phase explosion I spoke about before. This is in copper, and we've just got a whole ejected mass of molten particles, which will hang around on the surface and be quite problematic. You also see that if we're machining in these regimes, we're generating quite a nasty edge burr on some of our features, and we don't want to be leaving edge burrs like this around, okay? What we want to do is be able to take a process which might look nasty like this, where we've generated molten metal, and get it back to something with nice clean edges. And there are a few ways we do that. One is with the CNC routine we use, but also the trend to go towards shorter and shorter laser pulses. And you'll see many diagrams like this floating around the internet when you look up ultra-fast laser processing. And these are mostly from people trying to sell you the laser. So they don't tell the full story, but it's partway there. And I've got 3 of them just to show you an example. This is one. They talk about having a nanosecond laser, so a laser with pulses of tens of nanoseconds. Tens of nanoseconds is enough to conduct heat into the material over the duration of the laser pulse. And so what they often say with nanosecond lasers is you're going to make a mess. You're going to end up with recast material and surface debris. We're talking about lasers which get down to 10 picosecond and lower pulse, where the process is largely more, like I was describing, the coulombic explosion, can be more dominated by ejection of atomized vapor rather than actual phase change in the material. Here's another one. This is from IPG. They put a bit more detail in there, but same sort of theme, okay? This is what they're trying to sell us on. And finally, if it's in German, you know it must be true. Okay, so this is a German version from another laser company. We're essentially saying you want to be in this femtosecond, picosecond regime to be able to do these very clean features. The reality is it's not the full story. There's only so far you can push these processes. Just because you have a femtosecond laser doesn't mean you can process something with a femtosecond laser in hundreds of microjoules. That's, at some point you'll still be putting so much energy into the system that you will get molten effects. And I just have an example here from my work when I was looking at this, where we were just looking at everyone's favourite substrate, silicon, and seeing what happened as we started to push the pulse energy up and up and up. And as you can see, we start off with these single pulse craters, which are beautifully smooth, okay, not too much debris around. But soon as we exceed a few joules per centimetre, and that's a measure of the dosage on target, we then have a molten looking finish on the surface, okay? We're clearly creating a molten surface in the silicon. So there's only so far you can push these processes before you run into these problems which get you back into the same regime with nanosecond lasers. For that reason, these ultra-fast processes are not necessarily super fast. Sometimes you have to be patient with your laser etching. One of the approaches that you do these days, though, is try and scan the beam extremely quickly using galvanometers and things like that, and then use a lower energy, but scan many, many dozens of times to get the feature that you want. And that's where it differs from laser cutting. You saw at the start the laser cutting the steel, you know, you just turn on the flame and away you go. These processes are more akin to milling or etching often, okay? But we're doing it like in the reverse of 3D printing when you build something up from the bottom up. We're etching stuff from the top down by removing small layers of material each time while trying to preserve the quality of the feature that we're leaving behind. And this is some of the examples where we're doing this. Now, I used to give this slide talking about picosecond lasers because the femtosecond lasers to do this weren't really industrially reliable 10 years ago. But that's not the case at the moment. My next slide, I'll explain what we're doing. But these are the sort of quality features that you're getting with these ultra-short laser pulses. And in answer to some of the questions, like how can you do maskless etching and things like that with a laser, you can get away with prototyping, but you're never going to get the surface morphology as beautiful as you can with the DRIE process, for example. So what we've done for University of South Australia, some of the projects that happen here, is that we will often do the first glass prototype, because we can machine borofloat glass reasonably well, but we're still going to leave behind a 0.5 micron roughness finish, okay, which is not real nice when you're trying to look through it with a microscope or something like that. But if all you're after are some microfluidic channels, which do that, it's just as quick to get us to machine them up for the first couple, rather than have to go through the process of making up the lithography mask, doing lithography and getting it etched. So we've had several chips over the years where they've just come to us to put the channels in. We also do a lot of the via drilling, okay? So drilling vias through the 1 millimetre substrates or thicker. That's something that the laser does a lot, and that's where a lot of devices will come for a holiday with me to get their holes put in them. So you can think about doing some maskless prototyping with this, but you'll never reach the fidelity of process as if you do it with a full lithography and a DRE process. A lot of the areas, and I'll cover all the different materials we've done work in for people, but a lot of our day-to-day stuff is more in metallic components. So we drill nice nozzle holes, and we also cut some very nice features in precious metals like gold and platinum, things that are used in implants and the like. Okay. So in regards to where we're going, in 2012 when we first got our laser, it was running a picosecond laser from a company called Lumera. Since then, lasers have come a long way. Okay, this is a market which is very rapidly advancing. So what we're going to be looking at doing next year, we're going to upgrade our old picosecond Lumera laser, which gave about 8 picosecond pulses, and upgrade to a new class of lasers which have become mature in the last few years, which are femtosecond lasers which can scale up to 20 or 40 watts. Now, 20 or 40 watts may not sound very large to you when we're talking about kilowatt fibre laser cutters. The thing is in the peak pulse energy. Okay, so for 8 picosecond pulses, we're talking each individual pulse might have a peak power of 12.5 megawatts. Okay, that's the instantaneous power on target. That's why stuff subliminates when we hit it with these lasers. When we go an order of magnitude shorter pulse, down to 300 femtoseconds, say, then we're up to 330 megawatts of power in each individual pulse. That's an instantaneous power. That's going to break apart any material. It subliminates stuff. Lasers like this are also being developed on much larger scales to do fusion ignition and things like that. There's really some exotic physics that's being done with these lasers that they develop. But when we're doing micromachining, this class of laser that I have on the right now, and there are several companies doing it, just don't take my word that Light Conversion's the only company doing it, though they're a very good one. This is the sort of upgrade that we're looking at doing in the next 6 to 12 months to keep us at the cutting edge. Okay. So when you want to get something laser cut, the process flow is very much like you do with CNC stuff. And so if there's one of the pracs that you might sit around getting a bit bored in with Simon over the course of this week, don't, and Mark, yes, don't, get into the CAD part, especially if you're not familiar with having used AutoCAD or Inventor or SolidWorks before. The course that we can give you in a couple of hours here at the engineering school is only just going to give you a taste. But while you're at university, you can essentially get copies of the software for free, and I encourage you to try and master it, because whether you're communicating with the fab doing stuff with lithography or a laser cutter cutting you something out, you want to be able to draw and manipulate CAD designs, because that's the information that feeds the machine. Okay? So largely we will take 2D DXFs for our 2D process, and we will run them through a G-code converter. That's the language that machine can understand, and away we go. We can hit go on it. There are a few things we do. The next step on that is to do 2.5D processing. This is sort of like the etching we talked about. Here's some examples where we've got some microfluidic prototypes there. These were fairly large pillars that we were leaving behind in a fairly large channel. So that's a sort of area where the laser can be helpful. As well, we can do sort of semi-3D stuff. So this was a pair of slides which was meant to have a cavity there to hold an optical fibre between them. So you can go into 2.5D processing. Where we're going next year as well, this is our new machine, which is currently still under construction in Germany, but it's something we hope to get in the country at the start of next year. Be quite a unique machine in the Southern Hemisphere. This is a 5-axis laser machine which is going to use one of these femtosecond lasers. So you can see the carbide hiding in the back of the machine there on the left-hand side. I just have a very quick clip that I will hopefully be able to bring up flawlessly without an ad.
What could you do with a metal 3D?
All right, wait for the ad to skip. I just want to show a very quick clip on what 5-axis laser machining might look like and the sort of thing you can do with it. So this is from a company that builds the control software for these machines, DMC. And this is sort of what it looks like. This is showing the 5-axis gimbal and rotation stage. When you get to doing processes like this, you actually end up in a CAD-CAM model which simulates the whole machine and process. So this is going to be a learning curve for me. I'll probably be comparing notes with Mark at some stage about how all this stuff is supposed to work. But gives you some idea of where we're going with this. So this will be our new machine next year, which will actually take us into true sort of 5-axis processing, where we can mark and raster and drill holes in parts, hopefully from any sort of attack point. Okay. This is where I'll be really quick. Just some quick examples of real processes we've done. This is a bit of an old one now, but it does come up every couple of years as Damien wants to do these. This is a process that would be very tricky to do with lithography and etching, just because the substrates are 100 micron cover slip glass. And that's very fragile to try and put in a mask aligner. So one little example of something we do. Here we're drilling some little 25 micron pores through 100 micron cover slip glass. And with this, the group at Curtin is doing some liquid separation, because they will make one side of these pores hydrophobic and one side not, and they can do some chemical migration through them. The chemistry is up to them, but the processing here is something we can do with a little UV laser to make something that's very difficult to do otherwise in the clean room. Okay. You're going to go and visit Heike, and also I'll point out that those of you that get to go and see David Lancaster's lab here, I think, is that at Friday? Yep. Or this afternoon? Friday, I think. Yep. You'll see more photonic stuff being done with lasers. Okay, we do this sort of stuff at Macquarie as well, but David's also very good at this, so I'd encourage you to go along to his lab tour on Friday to see more about what this is about. This is a microstructured optical fibre from University of Adelaide, and what we've done, we've put a little Bragg grating, which is a periodic modulation on the fibre core, and we've done it with a femtosecond laser, and we've got features down here which are about 800 nanometres in size. The reason why I keep this example in, it just gives you an idea of the sort of process resolution you can start to think about, okay? We can put little dots and features on things which are sort of that 800 nanometre in size. That's sort of the lowest you sensibly go with these setup. This particular device was a refractive index sensor. Okay, so as you dip the fibre into different media, you get different resonances from the Bragg grating, and you can see there what they've done there. So this has evolved a lot since this slide, and hopefully you get a bit of a flavour from that from your visit to Adelaide, but also your visit to Dave Lancaster. Photovoltaics, you mentioned how about maskless etching. I can bring this up here. A lot of the photovoltaic stuff, you want to wet etch on your silicon. I just kicked myself off. You want to wet etch on your silicon, which gives you these pyramid structures. Okay, so it increases the surface area and the light absorption. This is an example of a maskless etch where you're just dipping the silicon in, and the natural nucleation points and pyramidal structure of the silicon lattice will give you these rough pyramid structures. Why I had this slide in terms of laser processing, this is one area where laser processing is really important to future developments, okay? And so a lot of photovoltaics, and the ramp up of photovoltaics is just incredible, the amount of this stuff being rolled out. But lasers are used often to mark out the bus bars for collection of the wafers and things like that. That's one example there. We do have several researchers from the big photovoltaic group at UNSW coming and using our facilities to do various things on their wafers. What? Sorry, guys. I'll be very quick now. Soft materials. We drill holes and cut features out of very soft materials, whether it's PVDF, which is a very soft gelatinous plastic, through to captans and things like that, which are often used in devices in clean rooms, as well as peaks are challenging material for catheters and things like that. We can also do very brittle materials. Now, this is not something that you'd want to do mechanically, and that's to work with graphites and coal and things like this. To give you an idea of scale, the feature that we're looking there on the left, the part on the left, that's about 1 centimetre, so that's 10 millimetres in size. A lot of the channels and bridges that we're leaving behind after laser machining are only 100 or 200 microns in width. That's very, very fragile when you're doing that out of pyrolytic graphite, but we can get away with it. So I guess that's one of the other key messages with the laser machining is that while there are some forces involved, it is a lot more, it's much closer to a non-contact process than machining and things like that. And you certainly don't want to be taking your dirty coal samples into the clean room to do lithography on them. So this is an example of maskless etching, but in a very sort of novel material that you wouldn't want to play around with. So as you can see, the coal example, they were looking at microfluidics of coal seams when they were under fracking conditions, which is very important when you're trying to demonstrate where all those nasty chemicals are going to go. So that's another example. We machine ceramics. Some of myself and Igor's first interactions was having us drill some via holes in ceramics for the guys in Edinburgh. These days we also cut small ceramic components for microX. I'll talk a little bit more about what we do for them to finish off, but also challenging materials like boron nitride ceramics and things like that. It's very difficult to machine, it's hard on the tooling, but if the features aren't too demanding, we can do a lot of work in the laser machining to get them by. And hardest materials. I'll skip past this one quickly. We can do stuff in diamond as well. Very hard to do with tooling. So one of the examples that I'll do quickly, what are we up to? 51, time's up, all right. Okay, have to be real quick then, because I'm keeping you from lunch at this point. An example of a flow through that brings together a few of the talks that we've gone through is a project like this. Okay, this is laser hydrophone substrates for DSTG. These wafers start off here at UniSA, where they need to be lithography patterned and then etched. And why they're being etched carefully is because the grooves in the middle you can see in the yellow layer there, they're there to support 125 micron optical fibres. So the etching is quite critical here, and you don't want to compromise that by trying to do it with a laser. But then these wafers come up to us for a little bit of a holiday where we're actually machining through slots through the whole wafer. Something that's very difficult to do is to etch through a whole 700 micron thick silicon wafer. And so the process will look something like this. And I'll just reiterate, enjoy your CAD practice this year, because that's the language when we're passing wafers around and we have to match different machines to them. The CAD is really instrumental in being able to do that. So we have to align on reticles which have been etched in and then apply laser features to the target. So our job here was to machine these slots through, which are about 0.4 by 17 mil long slots, through the whole wafer. And they're back here for dicing now, so we'll see how this goes. So this is an exercise in DSTG being able to trust other people to actually scale up production of some of the components that they've been developing, and it's quite a good thing to be involved in. Okay, I've run out of time, but I'll just say this is a very good company that's in your backyard. These guys are down at Flinders called MicroX. They've been we've been instrumental in getting their current products off the ground. And this is where what I do becomes really real-world applicable, okay? So MicroX makes X-ray tubes, and inside an X-ray tube, you need a high-voltage mesh to accelerate the electrons down the tube. And it's a very challenging thing to do. The material needs to be very robust, so quite often it's tungsten. And tungsten's a very tough material to machine. And they're looking, you can see my pictures down the bottom, they're looking at very rapid iteration of their devices to try to get stuff into production. And that's where the facility like we can offer them really makes companies like this get off the ground. The benefits of working with us is that we're local, we're responsive. You know, those guys are really happy when they can get something out of me in a couple of days when they're waiting 6 to 8 weeks to get something out of Europe. And we can be really flexible with the guys as they change their mind and stuff like that, whereas other suppliers will tend to get quite annoyed if they're having to reiterate and reset a process all the time. So this is a real-world success story of the sort of stuff that we've been able to do. And this is a company that, as you guys go through your degrees and postdocs and everything else, if you get a chance to do an internship or get involved with MicroX, hopefully they're going places because they're taking a lot of Flinders students and a lot of other personnel from Adelaide and put them into a really positive company. Okay, I'll skip over these. These were my videos, Michael Breadmore style. But we're out of time. We better let you go to lunch. These will hopefully be in the slideshow when I hand them over. And these are just examples of where this laser technology is used in advanced manufacturing and where the companies that put these systems going are really going. And otherwise, thank you very much. I live up at the Hearing Hub at Macquarie University. There's my email. If you ever find yourself needing a via hole or a mask cut out of brass or something like that, you'll probably end up talking to me at some point. So thank you very much.
Thank you very much, Ben. Don't go away just yet. Are there any questions for Ben? Yes, Igor.
Laser light energy can change the optical properties of material radiation microchip. Now, can you tell us how that affects the process?
That's an open-end question. So it really depends. So you're saying the laser light comes in, it modifies the material. Yep. Usually what I tell people, if we're hard machining something, if we're removing material, there will be some sort of skin layer in the bottom which is laser affected. And it will be different depending on the different materials. So for example, in glass we tend to leave behind an area of sort of amorphous glass. And that can actually be useful, you know. Some years ago we were actually interested in studying the wettability of those glasses and what happens when you try to etch them. In things like silicon, you'll end up with porous layers and things like that as well. So if you want a silicon which is going to be, you know, back to pure silicon, you're not going to want to throw a laser process at it. Okay? You want to use an etching process, for example. Where else could we take the conversation, Igor?
I was thinking if you change the optical properties of the material,
yep. Yep.
Right, and then your laser ablation yield all of a sudden decreases.
Yeah, there's funny things like that can happen as well. Yeah,
the optical properties are changing, like especially metals.
Yeah, there is funny. There are funny things. If you're really trying to process monitor the ablation efficiency, you can find funny things happen like the reflectivity change. And actually, processing can go up for some materials as well. If you start off with beautifully polished aluminium, your first couple of rasters is not going to be as efficient as the following ones because you're getting a lot more reflection off the surface. But when you go and look at, you can get funny effects too on metals with femtosecond lasers, where if you're machining very, very gently, you can actually get nano ripples, like self-aligned nano ripples, which are very pretty to look at. You see some of that, some of the colorization that comes up? Yeah. So there is a process called laser-induced periodic surface structure. It's a phenomenon that happens with these short pulse lasers. It is used sometimes by watchmakers. So if you look at a really expensive watch and it's got a whole bunch of rainbow iridescent stuff on it, quite often that has been put down by a femtosecond laser, which is creating a periodic ripple in the metal surface. So there are lots of different optical effects. It really is an open question, but conditions, as you're machining something, conditions certainly can change from one pass to another.
I'm going to jump in there because I mean that was very interesting, but I reckon you guys could talk for a very long time. Look, Ben, I want to thank you again for coming back to join us in Adelaide, and it's great to have you in person this time. It means I can give you a gift to say thank you, but I also just want to highlight to everybody here just what a wealth of knowledge we have in Ben, and so please tap in, talk to him. He loves talking about this, as you can tell. So grab him at lunch or in the breaks and ask him all your questions because you'll get some good answers. Let's thank Ben. Okay, we're off to lunch, but just a reminder, in about not much time, 10 minutes, those of you going on the tour, grab some food and eat fast so we can get you on the bus. Thanks, man. That's fantastic.
Oh, good.
Yeah. Just go to the meeting.